I had a number of students ask me for help on the calculations for activity 2 on the estimating Avogadro's number lab. So this lab right here. And this was my data table that I got, so I thought I'd go through the calculations I did with this data. And as I'm going through the calculations, I'll probably be referencing these numbers, but if you want to see the numbers that I got when I did the lab, here they are on my data sheet. The first calculation that I want to go through is figuring out the volume of the aluminum foil from the density. Okay, the volume is going to require that we know the mass. In my case, 3.00 grams if you're having trouble reading it on my data sheet. So using this mass along with the density of aluminum that's given to us, we can figure out what the volume is, and that's by using the simple equation that density is going to be equal to mass over volume, which means that volume is equal to mass over density. And so in our case, as you can see from my data table there, the mass of my aluminum foil was 3.00 grams, and like it gave it to us there, that the density of the aluminum foil or aluminum is 2.70 grams per cubic centimeter. One thing you're going to notice as I'm going through these calculations is the units are pretty critical throughout this, so it's important to be in the right units and be writing down all your units. And so when I do this calculation of 3 divided by 2.70, I'm getting 1.11111 repeating, and this is going to be 3 sig fig, so I'm going to put my line over the third sig fig there. And unit-wise, when we take grams divided by grams over centimeter cubed, our unit for the volume is cubic centimeters. And you can see as I'm going back to this very first slide here, the area of my aluminum was about 705 centimeters cubed, and that came from the length of the aluminum and the width of the aluminum. The next thing that we need to do, especially unit-wise, is change the radius of our aluminum atom into centimeters. It's given to us in picometers, which is a typical unit that you would give an atomic radius in, and it tells us that the atomic radius is 143 picometers. But you're going to see later on why it's so critical that we actually have this number not in picometers but in centimeters. So let's look at the conversion of that. We know that 1 picometer is 10 to the negative 12th meters. And then we also know that 1 meter has 100 centimeters in it, which means that our radius of our aluminum atom in centimeters is going to be 1.43 times 10 to the negative 8th, and again that unit is centimeters. And that's because in my dimensional analysis here, these picometers would cross out and these meters would cross out, leaving us with the centimeter. So using this information now, I can figure out the volume of one aluminum atom. So the volume of one aluminum atom, we're assuming that an aluminum atom is a sphere. The volume of a sphere is equal to 4/3 pi times r cubed. So in our case, that's going to be 4/3 pi times 1.43 times 10 to the negative 8th centimeters cubed. When I carry out that calculation, I see that the volume of my aluminum atom in cubic centimeters is 1.224 with a whole bunch of other numbers after it, and I just rounded that to 9 for right now, times 10 to the negative 23rd, and that's cubic centimeters, and that's because our unit of our radius was in centimeters, so when we cubed it, that became cubic centimeters. And now, knowing the volume of one aluminum atom and knowing the volume of our aluminum totally, we can figure out the number of aluminum atoms in the foil. So the number of aluminum atoms that were in the foil is going to be the volume of the foil divided by the volume of one aluminum atom. So remember, the volume of our foil was like 1.11, and it kept on going on, and that was cubic centimeters. And then dividing that by the volume of just one aluminum atom, which we did above there, 1.2249 times 10 to the negative 23rd cubic centimeters. These cubic centimeters are going to go away, and that should give us the number of atoms of aluminum that were in, or approximation at least, that were in our piece of aluminum foil that we had. So hopefully, if you're following along in my calculations, when you do this, you should get about 9.07 times 10 to the 22nd aluminum atoms that are in my piece of aluminum foil, at least. And obviously your numbers are going to be slightly different, and you're going to have slightly different answers here, but hopefully this will help you in figuring out, if you did do something wrong in your calculations, where you went wrong. And that was calculated right here, where we had our number of aluminum atoms. The next thing I did was determine the number of moles that I had of aluminum in my aluminum foil, and that was by using the mass of aluminum foil I had and the molar mass of aluminum. Remember from before, the mass of aluminum that I had was 3.00 grams of aluminum. And then using the molar mass of aluminum, I can figure out how many moles I have. We know that the molar mass of aluminum is 26.98 grams per mole. So the amount of aluminum then that we have is about 0.11119. So 0.11119 ... That's going to keep on going, and that's how many moles of aluminum I had. So then our experimental Avogadro's number will be the number of aluminum atoms we had divided by the number of moles of aluminum. So that should tell us how many atoms are in 1 mole of aluminum. And in our case, we know that the number of moles of aluminum was the 0.11119 that we calculated before, and the number of atoms we calculated on that previous slide, which was the 9.07 times 10 to the 22nd aluminum atoms. So when I do this in my calculator, I'm getting out that Avogadro's number, or the number of atoms in a mole, is about 8.16 times 10 to the 23rd. And obviously the real Avogadro's number is 6.022 times 10 to the 23rd. So at least I'm good with the order of magnitude here. My number here is a little bit off, but remember, this is all experimental data, and we've been doing some rounding and other things in here. The next thing I'm going to do is try to figure out how many atoms thick our aluminum is. And the way we're going to know that is first figuring out the thickness of our aluminum. Keep in mind that the volume of the aluminum is width times length times height. And the thing that we're really interested in here is the height of the aluminum, the thickness essentially. So if we can divide the volume by the area of our aluminum foil, that should leave us with the height or the thickness of the aluminum. So in our case, remember that the volume was about, or in my case, the volume was about 1.11 cubic centimeters. And then we're dividing by the area of the aluminum. So we figured out here that we had 0.00157 centimeters thick aluminum, and this is going to help us figure out how many atoms thick our aluminum was, which is going to help us figure out how many layers of aluminum atoms we had. There, if you remember, there is where we figured out the thickness of the aluminum foil, which was about 0.00157 centimeters. So knowing that information, the next thing that we want to remember here is that if we have an aluminum atom, and where that's our radius, the thickness of one aluminum atom is 2 times the radius. And so that should be about the height or the thickness of one aluminum atom. So we know that the radius of the aluminum is 143 picometers. So if we multiply that by 2, that's 286 picometers. But remember, we're doing so far everything in centimeters. So just like we did before, we need to actually change this picometers into centimeters. And we know that 1 picometer is 10 to the negative 12 meters. And we know that in 1 meter there are 100 centimeters. And doing this dimensional analysis should give us the height of one aluminum atom in centimeters. A little while back. So I just did the work in my calculator now. So the height of one single aluminum atom in centimeters is 2.86 times 10 to the negative 8th centimeters. So if we know the thickness of the aluminum foil, which we figured out, so the whole piece of aluminum foil again, 0.00157 with a bunch of other numbers after it, centimeters, and divided by the thickness of just one atom of aluminum, that should give us how many layers of aluminum we have in our aluminum foil, which I'm getting as about 55,051. And then this number goes on, 0.3. So that's the number of layers of aluminum atoms that are in my aluminum foil. I'm stopping this video now. I know that there is another activity with the stearic acid that you guys have to do, but hopefully the information I gave you in this video about the aluminum foil part of the lab will help you in the calculations. Again, as you're doing the calculations, be very, very careful on your units of things. So that's the thing that you want to be thinking about as you're doing this, because those units can really mess you up if you're not careful. If you keep things in the units that they give you, like picometers or things like that, when you actually need centimeters. You might not need centimeters in your part of the lab, but just be careful of the units overall.